Good evening. I'm Robbie Hothan. A little bit about myself. In 1986, I bought my first investment property, and since then I've been dealing with tenants and toilets. And but I also understood that energy was very important when I managed these buildings, and so I decided to embark on the path of education as far as energy. And so I enrolled in a master's program at NYIT on Long Island, and I subsequently received a master's degree in energy management. During that master's degree, I started exploring biofuels, and I ended up doing a thesis on vegetable oil as an alternative fuel. However, when I went to the biodiesel conference in Fort Lauderdale, Florida, January 2005, I couldn't understand why all the biodiesel equipment was made in Austria. So that got me to think, they must know something. Then I also learned that Austrians have houses that basically heat themselves. So I had to learn more. And that's when I started going. In 2005, I went to my first Passive House conference in Germany. And so, yes, as a property manager, I paid dearly each month for all the renovations that I did and managed in my buildings. But I paid for it, not only monetarily, however, I also paid for it with tenant dissatisfaction. I paid for it in reduction of longevity of the building materials. And I wasn't doing anything wrong. I was building to the minimum standards of the building code. So let me ask you, why would anybody want to do minimum standards? If you have a child in school, do you want them to get a D because D's passing? So Passive House does, Passive House basically is a standard that relies on building well and designed well. So Passive House has strict standards. They don't work, oh yeah, so if there's any LEED people here or any other green builders, we understand that in this country, we build 15% better than the average. Or we build 20% better. The percentage, that's all fuzzy math. In Passive House, we have strict guidelines to follow. We have a set criteria, and they can be easily quantified, and they are. So we have an annual heat demand of 15 kilowatt hours. Oh, excuse me, I'm sorry. But I don't know if anyone noticed it, but sometimes I speak in metrics. So just in case anybody wants to equivalent when I slip and speak in metric, this is a square meter. It's equal to about 10.75 square feet. But if you just round it to 10 feet, it kind of works out pretty easy. For example, when we say heating load, that means that the equipment, that means the boiler or the heating system, can only be sized as far as, for the coldest day of the year, at 10 kilowatts per square meter, which is about 1 watt per square foot.
10 watts?
10 watts, excuse me, thank you. 10 watts per meter, which is about 1 watt per square foot when we do that, when we do the metric conversion. A watt a foot. So if I have 1,000 square foot apartment, I could heat it with 1,000 watt hairdryer on the coldest day of the year. Also, the depressurization, a blower door test, as we had seen before. The blower door is a very crucial piece of equipment to help make sure that our craftsmen are doing what we're paying them to do. So far, there are no guidelines in most of our domestic codes regarding airtightness. In Europe, airtightness has been a very valuable building trade. And they have very strict standards, which are difficult to make, but now difficult for Americans to actually create. But in Europe, they're not building 0.6, they're doing 0.25. They're making them very tight. Okay, so I have a model of what all that would mean, you know, as far as insulation and air tightness. It's the igloo cooler. It's a complete envelope being very well insulated, and when it's latched, it's pretty doggone tight. So if you can take the prop away, thank you.
How many bottles of beer will it hold?
A couple of cases too.
And keep it cold for how long?
So, so they're using a software called PHPP, which is Passive House Planner, and we have inspections, including blower door testing, to make sure that we're constructing this properly, and also we can verify. See, it's also a lot of times it's difficult to verify how well we constructed our low energy buildings, but it can be done by using the PHPP, that's for the design element, and then the depressurization test, and then post-occupancy you could just read the utility bill. And so the basic concept is to use less energy, not make more. So passive house, as you heard, passive house is a very simple mindset. It's not easy to build, but it's simple. On your handouts, you have the 5 Grundprinzipien, which is in German, the 5 basic principles. And so first thing we have to do is make sure we have good insulation. This is a lot of review. So second is eliminating thermal bridges. So I don't know if we really covered thermal bridges, but there's a giant thermal bridge in this building right now. Can anybody tell me where that giant thermal bridge is?
Ceiling.
Well, we don't. Let's just assume that this roof is insulated on the exterior. Yeah. The chimney. It's penetrating the insulation barrier, and it's a giant thermal bridge. So that's an example of what a thermal bridge is. It could also be a bolt. Let's just say one of these posts go outside the thermal boundary, and that is also a thermal bridge. Passive house windows. That's really important because the glass being triple pane with an inert gas fill is we have created very good glazing in Europe. The next is the air tightness. So when you have an airtight building, then you limit your losses through convection, the movement of air. You increase the comfort, and you also reduce problems with mold. And then you can, when you have an airtight building, then you can make use of a heat recovery ventilation system, which you've seen already. So it's a holistic approach, unlike our other standards that we may have, where you get a point from column A and a point from column B, and you know what, C's too tough, we'll let that one out, and we'll go for D, and we'll get 2 points on D, okay, great. Except if you leave one of those points out, you negate a great opportunity to really reduce your energy consumption. So in this case, the whole passive house is greater than the sum of its parts. So this is a thermal image of a coffee pot. You know, the kind that we use here, and this is So how do we? Yes, you already saw the blower door, and so that's the formula. -50 is equal to or less than 0.6 air changes an hour. And I found this in Fine Home Building, May of 2010, and it made a comparison with Passive House, and the current energy code. Passive House, remember, Passive House for the air changes per hour was 0.6. Our code permits 7. But what about Energy Star? And by the way, I'm trained by Energy Star. In fact, I did only one in my life analysis. Energy Star permits 5 air changes. Passive house 0.6. Well, how does it compare to our code? So 475, that sounds familiar. That's the name of Sam's company. So 475, the amount of BTUs that's permitted to be used per square foot in a passive house. But how does that compare to our existing building code? Well, let's see, that's 10 times more than we require in this country. And, well, what about Energy Star? Well, Energy Star is a little bit better, but you know, you just spent all this money to create an Energy Star house. Well, why don't you just spend that money and build a passive house? So we've seen this graph before. This shows the investment in energy reduction, insulation, air sealing, etc. And there's a sweet spot at this point where you can eliminate your heating plant, which is thousands of dollars, and that money could be used to pay for your windows, it could be used to pay for your air sealing, it could be used to pay for your insulation. And then you notice that this is the passive house right here, but why does it shoot up like that? You know, up to very expensive numbers as we get closer to zero. Does anybody know why? Does it get very expensive after you get past the this is 15 kWh, 15 kilowatt hours per square meter. That's this point right here. Why does it shoot up?
You're not using enough to make all that expenditure.
Well, anybody else?
No, because additional gains come from having to massively increase your thermal insulation, better sealing.
Yeah, I think it shoots up like that because that's when you're putting on your PV. That's when you're putting in your geo exchange. That's when you're doing other very sexy things to reduce your energy. So the thermal boundary is very important. This is basic building science. When you get a cross section, a set of plans, you want to be able to define the thermal boundary with, you put your crayon in one corner and you slide it over and you show where the thermal boundary is, and then you continue, and it should not, your pen should, or crayon should never be lifted till you get to your other starting point, and that is important because that's how you have an igloo cooler. This also shows the ventilation system. So this is kind of interesting. The question came up before about the heat recovery ventilator. That's what this mechanism is. And in Europe, because they're blessed with mild relative humidity, that they're able to use things like an earth tube. And that's what this is. This earth tube takes in fresh air, brings it under the ground, and it's tempering the fresh air. So you get a little bit of energy out of the ground, it kind of tempers it a little bit, and then it sends it through the heat recovery or the energy recovery ventilation device. It takes that fresh air from outside and then exchanges it with the stale air, leaving the building. It doesn't ever mix, but it pulls the heat out, it exchanges the energy, and that means you get almost room temperature air being put into all the rooms that you live in. The bedroom, the living room, and then the exhaust would be exiting from the bathrooms and the kitchens. So, the saying is build it tight and ventilate it right. That increases comfort, increases the indoor air quality, eliminates the secondhand smoke, bed bugs, a big problem in New York City, because you're building an airtight barrier. Oh, by the way, there's also another color crayon that you would put and define your air barrier.
But wait, how does it affect bed bugs?
Well, if the bed bug can't get in your house, then it can't get in your bed. So if there's an air barrier, he can't penetrate the air barrier. I mean, unless you brought him in with, you know, luggage, yeah.
Bed bugs walk across the street to your house?
So what I was referring to was a serious problem that we had in some New York City apartments where bed bugs were infesting an entire apartment building. And it started with one apartment, but because there were chaseways and there was air passages all over, it was incredible, and it was a nightmare. And Peter is our bed bug resident
I
expert.
already answered the bed bug question,
Okay.
Now related, but it's
All right, hold all bed bug questions and direct them to Peter, because he's got a lot of experience.
But this brings up a different question. Like, in how, what I was saying here before is like building an envelope for an entire building, not necessarily an apartment unit in a building.
Okay, so each apartment should be compartmentalized. So everybody's breathing their own air. If they're gonna smoke, let them smoke. It's not gonna affect anybody else. It's only gonna affect them.
But also as far as if you're doing an apartment building, obviously, the insulation on the inner walls would be different than the insulation on the outer walls. So there's all these different factors you have to take into effect in order to get your passive house gain, right?
Absolutely, and that's done on, well, of course, the planning stage.
Right.
So the other benefits of having an airtight envelope is that you have a reduction in vapor transmission because if air passes through, there's water vapor in air, right? And so if air migrates into and through a building component, well then that means there's a possibility of moisture building up, subsequently causing mold. You have a sound reduction, you have energy conservation. Oh, and by the way, you get to use your ERV now because you have an airtight. ERVs don't work. ERVs or HRVs, they do not work in leaky buildings. And this is a photograph. I don't know if this can help explain, but it looks like, think of this is a cross section of a ERV. Well, actually, that would be a heat recovery. No, that's a heat recovery. And it's passing, you can see that the air never really mixes, but it's traveling through, it's like one of those wafer cookies, and it's you know, like corrugated cardboard, so the air can travel through there, but it never really mixes, but it transfers the energy. So this is a multi-family housing project, and actually that's low income. Actually, that's that's an affordable housing complex in Innsbruck, Austria, and I took this photograph last year. But notice these ventilation stacks. That's where the fresh air is coming from to supply the fresh air to the occupants in that building. Now this photograph is taken near, this was during the Passive House Conference in Duluth. This is a very interesting house. This is an American-style passive house, and it's also featured in the Fine Home Building 2010 May issue. So just to give you an idea of what they're doing over there, they have, again, we saw this on prior slides, but it's a good review, that they're reducing the thermal bridge. Now, if this was just a one 2x4 wall or one 2x6 wall, that 2x6 or 2x4 acts as a thermal bridge. In fact, if on a good day, if I have a nice difference in temperature between indoors and outdoors, I can show you where every stud is using my thermal camera. So that's why they offset these. They have a double wall. And notice how the foot is for frame of reference, how wide it is, because they're going to pack this with dense packed cellulose insulation. The spray foam is used to air seal. Again, here's another, yeah, scalp. Notice the boxes. These electrical boxes are plastic boxes, but we don't normally, I mean, in standard construction, you don't really see that. But the reason why they're like that is so that we could get that air barrier.
So is that dense pack behind netting, or? did you
Yes,
do
that
wet
was dense pack. That's dense pack back there.
As opposed to the wet application of cellulose?
Well, there's different ways of applying the dense pack. This is one of them where they string up the netting and then they pump it in. So, you know, a lot of this a lot of this passive house stuff is kind of boring because you're only talking about insulation, air sealing, and you know, windows and ERV and elimination of thermal bridges. I mean, how exciting, how sexy is that?
Very.
Well, that's what I like to hear. But just in case insulation didn't turn anybody on, or air sealing doesn't. This is sexy because this is a storage system. Now this doesn't make a house passive, a passive house, but it's all the other stuff. This is dessert. First you got to eat your vegetables. This is dessert. So now this is Minnesota, way north, and what they're doing is they have these solar panels, and they're doing solar thermal, and they're trying to store the whole winter's worth of solar energy in these tanks. So one of the other things we have to talk about is the windows and the doors. This door closes like a vault. It's made in Germany. It's got multiple locking points, you know, strategically located, and that's so that this door can have a nice tight seal. Remember, we're trying to get 0.6 air changes at a depressurization of -50 pascals. So also we're using the triple pane because not only because of the energy. Now it's also important to understand that triple pane glass is not solely for the function of reducing energy. It's also for comfort. I mean, when does that come in our conversation? But when do we talk and say, well, I want a comfortable house? But I don't ever really hear that. But in any case, having a triple pane glazing increases the amount of comfort. Because if you ever notice, in your own private homes, usually there's a radiator underneath every window. Why? Is it so that you have a place to put your furniture everywhere else? No. Why is there a radiator under every window? Well, because that's a cold plate. In the winter, that is a cold plate. It would be very, very uncomfortable. So now it's only a little more uncomfortable than it normally would have been without the radiator. So also the other piece about windows is that a lot of people get the feeling of, you know, I gotta call what's that 1-800 window guy? I gotta call him. We gotta get new windows because I feel this breeze. Well, you know what? A lot of times the breeze isn't really caused by the window itself. I mean, most of the double hung window. By the way, double hung windows should be outlawed. We should never ever install another double hung window because there's no way you can get an airtight seal on it. You need a tilt turn or the casements. So the windows, because they're in a cold, if you have a cold exterior temperature, you have a process of creating a convective loop. So what's happening is, if you have a standard double pane glass, the air that's next to that double pane glass gets cold. And we learned in 10th grade science that the molecules of cold air move slower, and that makes them more dense. So that means that air drops. But when that cold air drops, where does the air come from to fill in the space? The void that was just created by the cold air dropping. It comes from somewhere else, usually higher. It'll be the warm air coming to fill in that space that the cold air just created, and it hits the window, and then that drops. And then you have just created a convective loop. It's just going in a circle, and you're sitting here reading your paper. I mean, I have a double hung window. By the way, it wasn't Anderson, it was Marvin. I installed it. It's in the blacksmith building. I installed it. It's installed pretty good. It's a double hung. What can I do? But I can't sit there without a hat on. I need a hat. And that's because of the convective loop. So this is a schematic of how that passive house in Minnesota was put together. Now we're going to Germany right now, and this is a concrete slab that was freshly poured. This is the beginning of beginning of the passive house construction process. And notice what we have here. That is insulation, and it's about about 10 inches. That's 120 millimeters. 120 millimeters. And that is about of R40, because it's graphite enhanced XPS.
There's never a basement in Pasadena?
No, they have, oh, you can have basements. It's, you know, it's,
But they just need to sit on that. So
in this, well, you know what? In this particular design, there's no basement. If there was a basement, they would have the same insulation, except it would be on the bottom.
And
And
the
so-
walls?
Right here. Well, here we are. So we have 120 millimeters times 2. We have, you know, 2 pieces of the 120, 240, which is 9.4 inches of insulation, which is about an R30 or so. Actually, no, that's R40. Closer to R40. That is called extruded polystyrene, and it is graphite enhanced. It's the same insulation that our neighbors are using at the Greystone building, except not nearly as much. They're using 2 inches. So here's some disturbing news. And I just got this email from the supplier of XPS, or the manufacturer of XPS, and it says, due to the increased cost of raw materials, that we have to raise our prices by 12% starting April 2nd. So if you need XPS, you got to buy it now. The problem, now why is XPS, well, it's not just XPS.
Oil.
Right, it's oil. It's oil. So, this is the crucial part. If we're going to build a passive house, do we do it when oil is $4 a gallon, or what is it now, $110 a barrel? $110 a barrel? Or do we wait until it's $200 a barrel? Because if we wait until it's $200 a barrel, you're not going to be able to afford it.
Robbie, what about recycling all that styrofoam? People throw away. And packaging your styrofoam? Why
The-
can't that be part of the production?
It does, but you know, it's that's a whole other entity. That's Passive House 401. So when energy is valuable, like it is in a passive house, or like it is in Europe, you'll notice that every pipe on the heating distribution system will be heavily insulated. This is like some of the best insulation around. It's called Armorflex.
It's called what?
It's called Armorflex, and the guys and the craftsmen who put that on, it looks, I mean, really, look at that. You cannot find Armorflex installed like this in this country. Whoever put that on must have been a tailor.
And what type of material is that?
It's
Is it foam, or, I mean,
it's like help us out. Okay, great.
it's like a neoprene.
It's like a neoprene foam. So I know I just thought this was really cool because I haven't seen one of these in a long time. But yeah, and I have
That's not a solar dryer?
yeah, this is a solar dryer. So you'll notice the passive house. A lot of passive houses have balconies, and the passive houses have balconies, but they aren't.
Tomatoes!
Yeah, but they are not part of the slab of the structure, because that slab becomes a giant thermal bridge. But we see it all over. But you'll notice that the passive houses will always have a balcony detached from the house, separate from the flooring system. And so, and you can kind of tell because they'll have the columns, and so that'll show you that it's not really, that it's suspended on its own. Again, we heard from the other presentations that one of the problems with having a very energy efficient and tight house and very good windows is that in the summertime, there's a tendency to overheat. And therefore, notice that the shading devices are on the exterior, because the exterior is the place to reduce the thermal gains, not the interior when the sun already got into your house.
So you're shading the structure as well?
So, well, this overhang is shading the structure in this instance. But it's really especially necessary for the east and west facing windows, because that's the real danger of overheating. This is also another passive house, and I don't think, you know what, they don't care if it's east or west facing. They're just putting those shading devices everywhere. So now we have another passive house. This is an office building, I believe, and they're putting insulation on the exterior. And again, this is massive insulation. It's on the exterior to speed installation and to avoid thermal bridges. And in closing, this is like the greatest. This is the greatest slide. This is the greatest slide because no, it's better. It gets better. Watch. I had taken my passive house exam in Germany, and when I came out of this conference room where I took the exam, I came out and I was like, oh God, how appropriate. And then I took a closer look, and I saw that. I was like, wow, cool. And then I turned my head and looked at the homepage and read that. I was like, oh my God, isn't that the truth? So. Any questions?
What's the news for those of us in an old house? We're not going to build now.
Yeah. Sam, what do you think?
Are you going to do construction?
Huh?
Are you going to do construction?
I did that 12 years ago.
Yeah, that's the problem.
The truth is, if you do a payback, it's just going to be expensive. It's going to be 40, 100 years. You're just not going to recoup it. As it's even.
If you're not planning any major, re-siding, re-roofing, none of that. So then it's probably more a weatherization job. And there are government incentives, there are organizations that do weatherization really well. You can, just by air sealing and insulating your attic, you can save a lot of energy, you can do it cost effectively.
And have a blower door test done.
If you email me, I'll direct you to some more incentives.
Yeah, you have a bed bug question?
Could you please, a lot of what I understand or what I do with passive houses, I insulate on the outside of my structure walls. And can you explain the benefits of insulating from the outside, but also how it speaks to what we brought up before in this room was about the thermal mass and also about air conditioning
Yeah, absolutely.
loads.
Okay, so the thermal mass of these buildings, actually, you notice, that's the problem with the ICFs. Anybody familiar with ICF? Insulated concrete forms? You build with them? So the ICF is a really, I did this concrete tour in Kansas City, and I saw all these ICF houses. I was like, wow, this is the way I want to build. But then I went to Europe, and they're like, what for you want to do that? I'm like, why? What do you mean? The insulation is on the wrong side. You don't want to insulate yourself from the, the ICF has ICF looks like a Lego that you fill concrete in, right? So it's a form, and it's made out of insulation. It's made out of rigid EPS foam, and you just stack the blocks. So it's so easy. You could build houses like anything, and then you fill it with concrete. So it's a concrete house, except the insulation. There's a little bit of insulation on the outside, and there's a little bit of insulation on the inside, but all the thermal mass is buried in the middle. And so you just separated, you decoupled yourself from that thermal mass, which could be a very powerful benefit for cooling, to keep your house comfortable, to keep your building cool, and for really energy storage too, and moderation, so you don't get the giant swings. So that's the benefit of exterior insulation. You're going to be hear a lot more about exterior insulation because the Europe, everything that's over there is going to eventually get here, and it's big over there. They're only doing exterior. Unfortunately, we associate exterior insulation with EFIS, and we've had lots of problems with EFIS in this country. EFIS, exterior finish insulation system, EFIS. That's the way you see that these guys, they staple this insulation onto the exterior of the building, and then they take a pail of mud, and then they parch the building with it.
I think of it as vinyl sided exterior insulation.
You're not going to vinyl side that.
There are quite a few landmark buildings being retrofitted to passive house from the inside as well.
But it's not easy.
You don't get as much massive, energy storage, but you do it from the inside, and it takes a bit more time and consideration. So, pick a side, but one's easier than the other.
Nobody seems to, how do you address the fact that you'd be using up so much square footage and volume of space by having the extra thick walls or having the entire, ductwork system inside the building? 200,000, 2 million square feet of New York City space, you're going to lose a lot of square footage.
That's a very good point, and that's another reason why we need to start the conversation talking about exterior insulation, because then you don't lose the square footage.
I did a retrofit of a townhouse, and it was the same framing dimensions and same wall thickness. Because of the shared wall situation, the R value was less. It was a 5.5-inch wall framed on the inside of the brick.
That's on the shared wall.
No, that was the exterior walls.
That's the exterior.
Yeah, there was no square footage change to the building.
And that's because in the PHPP, the calculation said, oh, we don't have a delta T between the two apartments. There's no difference in temperature, so that means we could minimize. It's like a balancing act, and so we don't have to load up the insulation on the.
That was multiple apartments in that?
That was one townhouse with an exact fit, single family 6-story with an exact fit to two neighbors.
And actually, that zoning in New York City, they just permitted buildings to insulate on the exterior, go over your building line. Yeah, and the zoning concessions for insulation.
It's under consideration. It's almost there, but not quite. Oh, good.
Just now.
Today, yes.
Oh, it passed today?
Well, it's almost there. I think
Yeah.
Regarding long-term care and maintenance, now, the idea of if you've got the efficiency is determined by it being perfectly energy sealed and air sealed. Over time, there might be some kind of break or disruption of that seal. How is that dealt with? Or does it ever occur? And then the other thing is, like I noticed on that one of the diagrams you showed, you had pipes going under the house.
Yeah, they do that in Germany. We don't do it so much here. I mean, I think it's been experimental, and we get condensate. In this country, we have a relatively higher humidity, and so we're taking warm, moist air, bringing it under the ground. Then the water condenses, and then you have issues. So we're not really doing that so much.
But to me, the issue is like a neighbor of ours has a forward-thinking person who did a heated driveway, and that thing is malfunctioning, and they can't get into it without tearing up the whole driveway. So when I saw that one example of the house, you got pipes going under the house. So when you have that kind of infrastructure, do you have a way to get to it to repair it if there's a malfunction?
That particular pipe that you saw there, although it looked like it was under the house, that's an earth tube. It's usually out in the garden.
Okay.
Can I address that too?
Okay.
So, I'm just going to speak loud. So, the question was about airtightness and durability of the components that keep the building airtight. It's actually a very important design issue. It's not a given that it works well or durably. And so, and it's quite common to go back and inspect old air barriers and find that they're much leakier than when they were first built. And so the air tightening product market that's developing in Europe is one way that's being addressed. Developing tapes and adhesives and sealants and membranes that have 50-year or longer lifespans. Yeah.
And of these older houses that are sort of broke, are they repairable in a good way?
It's part of design. So one very popular and cost-effective way to air tighten is called the drywall air barrier. So you use the drywall as the air barrier, and you seal the electrical boxes to the drywall, and you seal all the holes in the electrical boxes. And that, if there's a penetration in that, then you can access it, right? It's on the inside of the building. If it's buried in the wall, it's protected from damage in a certain way, but it's also harder to access.
There's a lot of experimenting going on with U.S. products to obtain air sealing, and there's a lot of failures going on. So there's kind of a saying with the past community that the first one doesn't count, because that's where you get your PhD and what's screwed up. So yeah, it works, but A lot of the stuff that's on the U.S. market just doesn't function. To be honest, I'm in a company now, which that's exactly what we address. We go get the European product that actually works. So, designed for the house. And it's got,
Can you explain, so the passive house being so thoroughly, let's say, conductive that it's really taking all this energy within, and we're using, I guess from what you're telling me, undersized units that are very efficient. How do we manage?
properly
You
sized.
said 3 tons for.
Properly sized. It's actually too big.